turn the the application screen so you can see all of you what I'm presenting. And this is the one that I'm presenting, right? So let me, everybody can see the slide, right? Yes or no? Let me know. If someone let me know. You can see the slide.
Yeah,
Yes?
please, yeah.
Thank you.
Yeah.
All right, very good. So let's go to, okay. Let's go to the, so basically remember what we did last time. I'm just probably repeating some of those, but that's okay. Repetition is good, right? So when n equals 3, we're making the elements of the group 3 elements and group 7a elements. And that will become basically what you have. You have a M3 plus, right? It's a group 3 element. Please turn off the microphone. Someone's microphone is on. And then group 1a, group 7a is X minus. Remember, X could be fluorine, chlorine, bromine, iodine, right? Fluorine, chlorine to the halogens. Chlorine, bromine, and I. That's a B, huh? That's big B, huh? All right. So if you have a M3 plus, that's a group 3A, right? 3 element make 3 plus. That could be aluminum, gallium, indium. And if you make a X plus, so remember you have a 3 pluses and 1 minus. So that means you have to use 3x minus. So therefore, it will be mx3. All right. So that's what you have: aluminum chloride, AlCl3, gallium bromide, GaBr3, and indium fluoride, IF3, etc., etc. Everybody okay, right? Likewise, if n equals 3, group 3 elements, M3 plus, same thing, right? M3 plus, and then we are doing the compound with group 6 element. Group 6 elements includes oxygen, and oxygen is 2 minus, am I right? Oxygen is 2 minus. Just give me 1 second. I'm skipping my cursor again. I have to do something. All right. So let's say this is 2 minus. So therefore, what you have a 3 pluses and 2 minuses. So what do you do? So what you need to do, you have to make a crisscross. These 2 will go to underneath the M. These 3 will go to underneath the O. And by doing so, what is going to happen? Let's see. So M2, O3, right? So M2, 2 of them M, 2 times 3 plus is 6 plus, and 3 times 2 minus 6 minus. So basically, M is the metal, by the way. So you get the metal oxide. So likewise, aluminum oxide, Al2O3, right? Aluminum oxide, gallium sulfide, Ga2S3, etc., etc. So you can make the compound like this way. Everybody okay? All right. So that's basically ends our ionic compounds and common ionic compounds from group 1A to 3A plus group 7A to 5A or 5A to 7A, either we want to say it. So these are the common elements. Now we'll go to some compounds with a polyatomic cation and anion. We have only one cation, that's ammonium ion, and anions are enormous detail. There's so many of them. So I'll give you the, I sent this slide to everybody, but we'll do some. Let's see what you did. Now we can make the compound and the name. I gave the name and you have to make the compound. Who can give me the formula of aluminum sulfate? Give me the formula of aluminum sulfate. Can anyone give me the aluminum sulfate formula of aluminum sulfate?
Is it Al? Go ahead.
Al?
SO3.
Huh? Al, SO. So let's write down clearly. So Al3 plus. Is it right or wrong? Yes. And SO4 2 minus. Now tell me. Now tell me the formula.
Is it Al2 SO4 3?
That is correct. That is correct. Al2 parenthesis, because sulfate is the one unit. So SO4 and 3. That is correct. That is correct. So L2, so you have a 2 of this and 3 of this. 3 of this. That is correct. Why? 2 times 3 plus 6 plus 3 times 2 minus is 6 minus. So L2SO4 whole 3. That is correct. That is correct. How about ammonium phosphate? Who can give me ammonium phosphate? Give me the ammonium phosphate. Your microphone is not clear. Tell me again, please. So ammonium NH4 is it right? NH4 plus 1 plus. And phosphate, what's the charge of the phosphate? Anyone? Phosphate, what's the charge?
3 negative.
3 minus. That's right. PO4 3 minus. Now put them together. Now tell me. So ammonium ion plus phosphate ion, put them together. You have a 1 plus 3 minus. So you have to take three of them. Am I right? You have to take 3 of them. So that means NH4 parenthesis 3 and PO4. That's ammonium phosphate. Everybody comfortable? Everybody okay? All right. Who can give me aluminum hydroxide? Give me the aluminum hydroxide. Aluminum hydroxide. We already did the aluminum. Let's do the gallium. That's fine. Let's do the gallium hydroxide. Gallium hydroxide. Give me the gallium hydroxide.
Is it GaOH3?
Excellent. Or you have to say the parentheses also. Oh, yeah, AH. That's correct. That's absolutely right. Yeah. How did you get it? 3 plus and OH minus is 1 minus. So 3 times 1 minus is 3 minus. That's right. Gallium hydroxide. Excellent. Excellent. Now let's do something Q+ chloride. Let's do the magnesium. Magnesium hydrogen phosphate. Can you give the magnesium hydrogen phosphate? You will practice the rest of them. You have to do it. Okay. Can you give the calcium magnesium hydrogen phosphate? Someone?
I have a question about this one too. But is the answer like HMgPO4?
Is
Or
it
does
one
it
unit?
have?
Yeah,
What?
it's one. Yeah, it's 1 unit. So magnesium 2 plus. That's very good. So hydrogen phosphate. Sorry, hydrogen phosphate HPO4. HPO4 2 minus. Yeah, that's a 1 unit. That is correct. So now tell me what is the formula of magnesium hydrogen phosphate?
Well, that's kind of like what my question was. Like, do you have to like put it in alphabetical order so that it's like HMgPO4, or do you
No,
leave it
no,
like MgHPO4?
metal fast. Very good point.
Okay.
Metal fast. And HPO4 is a unit, by the way. This is the 1 unit. You cannot separate them. So magnesium metal fast. Yes. So MgHPO4 altogether. 2 plus 2 minus. Very good. All right. That's very good. Now do the calcium phosphate. Can you do the calcium phosphate for me? Calcium phosphate. Give me the formula. Directly formula. Calcium phosphate. You already know the phosphate charge. You know the calcium. What's the formula?
Hey, I have a question real quick.
Yeah.
Do we have to memorize these?
No, you have the periodic table. Oh, yes or no? Metal ions, you can get it from the periodic table. The non-metals, the polyatomic anions, you have to remember that I marked it there. Yes, that is correct. But the metals, you get the periodic table, so you can use it, and you can get the symbol as well as the charge. That is easy. But non-metals, you have the polyatomic anions, you have to remember some of those. Yes. Now tell me, huh?
You
Yes,
said the quiz is multiple choice, right?
it's a multiple choice. Sure. All right. Calcium phosphate. Who can tell me quickly? Oh, sorry. Calcium phosphate.
In parentheses PO4 and then 2.
Excellent. What's your name? Very good. Yeah. Very good. Very good. Did I write okay? Did I write is okay? What you said? Yeah. All right. So that's the calcium phosphate. Very good. Very good. All right. Now do this one. Sorry, just a second. All right. Let's see. Ferric carbonate. Can you do the ferric carbonate for me? Ferric carbonate and sodium bicarbonate. Do that. Ferric bicarbonate. Who can tell me the formula? Molecular formula. Fe is a 3 plus, right? Ferric, ic. So that means it's a higher charge. Ferric 3 plus and CO3 2 minus. Now tell me, So you have to write down clearly first. Huh? If you write down side by side, then it will be easy for you to get the formula right. Tell me now. Can you tell me now? Come on.
Fe2 parentheses CO3 parentheses 3.
Yeah, just a minute. So Fe2, right? That's what you said?
Yeah.
CO3 parentheses 3, right? That's what you said?
Yeah.
Thank you. Very good. You're very good at this. Excellent. Excellent. Sodium bicarbonate. Who can tell me the sodium bicarbonate? Because it has a good use, right?
HCO3.
H.
No, Na.
Uh-huh. NaH.
HCO3.
Very good. Very good. And that is a baking soda. That's a baking soda. It is sold as a baking soda, and many people use it to make the dough for the bread or pizza, etc., etc. Because once you heat it up, you get the carbon dioxide. Just you get the fluffy. Many people use the sodium bicarbonate. Used to use, not nowadays, to as a honey. If you have acid reflux, acid reflux means you have acidity in your stomach. Then some people used to use the solution of that. It's a bit dangerous because once it goes inside the stomach, it makes the sodium hydroxide, and that can lead to the ulcer in down the road. So that is not good. Nowadays there are so many other things out there. Very good. So everybody is okay with it, right? Everybody is doing okay. Everybody is all right with the comfortable with this kind of formula. Question?
Professor
Yes?
hasn't even showed up.
What's the question? I didn't get it.
So how to freaking get into the exam because we have to download the stupid thing.
I cannot.
Is
I
it
don't think I can.
Proctorio?
Huh? Say it again.
Well,
All right, you're talking yourself probably. Okay, I'm going to move on. So I practice the rest of them, okay, during this weekend, because there's some of the questions to be asked from here. There are quite a few.
My question is, so if I have a proctor, do they just need to like be in the room while I take the test and I just email their signature and picture?
I will give you the proper instruction in the answer sheet. So basically what I'll do, I'll send you the question, the test attached to the email, and in the test, I have an answer sheet. In the answer sheet, I have a place for the proctor signature, proctor picture, and the
All right.
relationship with the proctor. Yes, please.
Thank you.
Yeah, you're welcome. All right, let's go on. Let's go on to move on to the next, okay? All right.
And about
Yes.
so do we have to go on Kent State campus to take our test?
No, you can use the proctor at home.
Oh, okay.
I'll send the test in your email, so you can get the test with the email.
Okay. Thank you.
All right.
How
Let's
long
go
are
to
we
the-
going to have for the test and how many questions is it?
And is it possible? Can I talk about on Friday? Yeah. Because let me finish it, whatever I'm supposed to talk. Today is Wednesday. So once I finish it, then Wednesday I'll give you the detailed instruction, everything there. Any question you have, I'll spend quite a lot of time along with the topics, question types, etc., etc. Is it okay?
Friday is perfect. Thank you.
Yeah, so you can remember. Very good. All right, let's go on to that. So far, if you recall what we have done so far in terms of the chemistry concept, we have done the metals, non-metals. We have identified the metals and the non-metals in the periodic table. We know which metal will become what charge, +1, +2, +3, or some variable charges. Those are transition metals. Non-metals, what charges they will become once they accept electrons. You also know that. Now you can put them together and make a compound. We also know the charges of the metals from the periodic table. And then you also have some polyatomic anions and cation, only one, ammonium one. And then you can also make a compound. They're all ionic compounds. So now we'll go to the properties of ionic compounds. Properties of ionic compounds. So properties of ionic compounds, usually one of the most important properties of ionic compound is the solubility. Solubility in water. So solubility in of water, water is a solvent, and many of the ionic compounds are soluble, some of them are not. And that's basically what we're going to find out. So when you take a ionic compound and put in a water, then what will happen? For example, if you take a table salt, the sodium chloride, take a pinch of it and take a glass of water or a cup of water and mix it, and it's gone. So that means they're gone? No, they're not gone. They're soluble. So what happened there? That's basically going to answer the question. In fact, what will happen, those cations and anions split. Cations and anions make compound, right? Join together to make ionic compound. Once you put them in water, then they'll split into cations and anions. Now, do they stay as a cations and anions? Or what is the structure of those cations and anions? That's what we'll talk about now. So that's the properties of the ionic compounds. Now, once again, when ionic compound, any kind of compound is dissolved or added to a solvent like water or some other things, and if they don't completely dissolved, completely gone, like sodium chloride, they make a solution. So solution is basically, in general, what you have a solute. Solute is the ionic compound. Solute is the ionic compound plus solvent. You add the solvent. Solvent is the one is a more major component. Solvent, just like water, and basically you end up with a water in the solution. So solutions are if you add the solutes plus solvents, and you get the solutions. So that's the solutions. Now, as I said, as I underneath right here, not all ionic compounds make solutions. So there must be some sort of generalization that will tell which molecules are soluble, which molecules are not insoluble. Insoluble means they don't dissolve, right? So that's basically the next. And this is the characteristics of the soluble ionic compounds. Once the soluble ionic compounds is dissolved in water, they dissociate into cations and anions, as I told you earlier, right? So if this is the general formula.
Can you go back for a second?
So sure. Let me tell me when you're done. Just a minute. I have to do something. Cursor. All right. Okay. Tell me when you're done. Okay.
I'm done.
Oh, very good. So when you take a general molecular ionic compound, MnAm, M is the metal, A is the ions, and then once you add the water H2O, and then go to N number of metal cations and M number of anions. Cations or anions are split. And these cations or anions are basically coordinated by AQ. AQ stands for the water. AQ stands for aqua. Aqua is the water, right? Another name of water is aqua. So each cations are basically coordinated or surrounded by water molecules. How many? 4 to 6. That's the average number. 4 to 6. Some cases 4, some cases 5, and some cases 6. So 4 to 6. Likewise, the anion is also coordinated by 4 to 6 molecules of water. That's called coordination. So once the metal ion is surrounded by the water molecule, and anions are also surrounded by the water molecules, they cannot add together anymore, because the water molecule will neutralize the charge of the cations and the anions. How do they do that? So let's take an example. So let's say example is our NaCl, right? NaCl, sodium chloride, and you add some water to it, H2O. Very good. And once you add the water to it, then we'll have a sodium, Na plus, and let's assume that we have a H2O, 6 of them, or let's say 4 to 6. That's basically the coordination number, right? 4 to 6, 4 to 6. All right. Plus Cl minus will have the same thing. Cl minus, and Cl minus will have a H2O, and you have a 4 to 6 water molecule. All right. So now, how does it look? If you look at the very in a structural form, it looks like this. So I'm going to write here. Just a minute. I'm going to write here. So you have or maybe let me take it. If I can take it to the, what you call, or maybe not. I can write it here probably. Let's okay. Oh, come on, give me. So we have, let's say, Na plus. All right, and O, oxygen, has a water H, one water molecule. You can have another water molecule like this, H, and H, I'm writing 4 just for the minimum number. So this, not to make it too crowded, and the water H2O, right? And let's put another one right here. Everybody can see it, right? What I'm writing, and you must, because this is a very important one, and there will be a question asked from this. So now 4 water molecules are surrounding. Now, how do they stay together? Remember, you have a metal ion is a positive charge. In principle, oxygen O is a delta negative, and I'll tell you again why it's a delta negative. So oxygen is a delta negative. Delta negative means small amount of negative charges. That's basically delta negative charge means. So you have oxygen is a delta negative, and so delta negative, delta negative, delta negative, delta negative. So what will happen? You have a positive charge there. Now they'll make a bond. They'll make a bond. They'll coordinate like this. So that's called coordination. That's a coordination. All right. So everybody okay, right? Yes. Tell me any questions. And that's with there are 4. I wrote 4. It will be 5 or 6. So that's a coordination. So this bond is basically, excuse me, this basically bond is made from the oxygen O, which is delta minus. So the cation is surrounded by this cation and the water molecule. And this is so basically what you have if you take a sphere. Water molecule is surrounding the cation, and that is called hydration shell. Shell, right? It's a cover. Yes.
Oh, I have a question. So the reason that they stay together is because the sodium has a positive charge, and so the negative charges from the oxygen in the water molecules, like, not bond, but they're attracted to the positive charge.
Yes, absolutely. Positive, negative attracts, right? The opposite
Right.
charges. Yep.
But
yep.
you
Right.
said that it. But if there's 4 oxygen, doesn't that mean that there's 4 negative and 1 sodium?
No. It's not a discrete negative charge. It's a delta. Very small amount of negative charge. Very small. It's not an absolute 1 minus. No.
Okay.
No. Yeah, very good point. Very good point. Yes. No, it's not. So that's hydration shell. Now, tell me, if you have a Cl minus, how will it coordinate to the water? It's a minus. It cannot coordinate to oxygen, right? So how will it coordinate to the water? Who can give me some idea? Yeah. So in fact, water molecule has oxygen is a delta minus, and hydrogen is a delta plus. Hydrogen is a delta plus. So both hydrogens are delta plus. All right, and I'll explain to you why they're delta plus and delta minus. So oxygen is a delta minus, and hydrogen is delta plus. So now tell me how it will coordinate the water molecule Cl minus.
With the hydrogen?
Yeah, of course, absolutely right. So now I'm going to write like another one water molecule. This is the delta plus, right? And likewise, let's say another hydrogen, another water molecule right here, OH. Please write it as good as I can. I'm using my cursor. That's and delta positive. Delta positive is small amount of charge. And another H. Let's write this side, and that's a water molecule like this. All right, and delta positive here, delta positive, and another hydrogen probably let's say right here. Okay, from water molecule. Yeah, absolutely. All right, so that's a water molecule, and hydrogen is delta plus. So therefore, that will make a coordination bond like this. So this will make a coordination bond like this. This one will make a coordination bond like this. This hydrogen will make a coordination bond like this, and therefore it will make a sphere, the hydration shell. So basically, all cations and anions are. This is an example of sodium chloride. You can have a magnesium chloride, you can have a calcium chloride, zinc chloride, any kind of ion, aluminum chloride, any kind of cations will be surrounded by water molecules and will create the hydration shell. Cation will be surrounded by the water molecules. Oxygen is directed towards the metal ion because oxygen is delta negative. And the counterpart anion will be directed by the H delta plus, the hydrogen. And that's how they make the hydration shell. Very good point. Why do they make the hydration shell? Why the oxygen is delta negative and hydrogen delta positive? Because when water molecule, question? So in water molecule, what you have HOH, right? and this is the covalent molecule. We'll talk about very soon. And oxygen is a group 6. So group 6 means it can take the 2 electrons very quickly to become a negative charge. So it has the higher affinity for electron. It loves the electron, and therefore it can make a 2- very quickly to become octet structure. That attraction of electron is known as electron affinity or electronegativity. Wait a minute, just a minute. Electronegativity. So electronegativity is the attraction of electron of a particular atom within a bond. So in this bond is shared by 2 electrons, one from hydrogen, one from oxygen, and one from this, and most of the electron density are towards oxygen. So therefore you have like this. So that's the arrow, huh? That's the oxygen. Electron clouds are surrounding, going towards the oxygen. Therefore oxygen is becoming delta minus. And by default hydrogen is delta positive then, because those electrons are going towards the oxygen. So hydrogen is delta positive and oxygen is delta negative. And in principle, the electronegativity of oxygen is 3.5. I'll give you this one. I'll explain again when we talk about molecular compound. En stands for electronegativity. Electronegativity of oxygen is 3.5 and electronegativity of hydrogen is 2.1. And so 2.1 is less than 3.5. Therefore, electrons are drawn towards oxygen. Oxygen become delta negative. Hydrogen become delta positive. Because of that water makes the polarity polar. Polar is a polar, 2 poles, 2 dipole, negative pole, positive pole, negative pole, positive pole. That's why we make a 2 dipole. And because of the dipole, now it can surround the cations and anions. And when they are surrounded, they basically partially neutralize this positive charge and negative charges. Therefore, this cation and anion can no longer attach together. They cannot make it NaCl. Now, water is a solvent. It provides some energy. It provides some energy to break the bond. Remember, Na plus and Cl minus, there is a bond there, right? Attraction there. That's called ionic force, an ionic bond. And this ionic bond is broken once you add the water molecule. Water provides the energy which is known as solvation energy. Solvation energy. S-O-L, solvation, V-A-T-I-O-N. Solvation energy. Solvent, what is a solvent? So it is solvation energy. S-O-L-V-A-T-I-O-N, solvation energy, E-N-E-R-G-O-Y, right? So solvation energy, my cursor is very, okay. Solvation energy. Solvation energy, it provides the solvation energy. So water provides the solvation energy to soluble ionic compounds to split the ionic force or ionic bond to generate cations and anions. Then water molecule surrounds the cation via oxygen. Water molecules surround the anion via hydrogen and neutralize the positive and negative charges respectively. And because of that, they can stay separated. And as they are separated, they create a solvation cell or hydration cell. So everybody okay, right? So here you go. Here is the explanation. Oxygen is more electronegative, meaning attraction of the electrons, than hydrogen. Therefore, the charge on oxygen is delta negative, small charge. Hydrogen is delta positive. So the oxygen atom forms the coordinate covalent bond. That's the bond is called coordinate covalent bond. Coordination, coordinating towards the cations or anions. Coordinate covalent bond with the cations, and hydrogen makes the similar bonds with the anions. Usually cations and anions are surrounded by 4 to 6 water molecules. How do you know 4 to 6? What basically people do, they take the ionic compound, dissolve in water, crystallize, make a crystal, and look at under the very powerful microscope we call X-ray crystal structure, X-ray crystallography. That's a machine will tell you that how many water molecules are surrounding the cations and anions. So it is just a number that you have to remember, and it is done by the X-ray crystallography. Okay. All right, I'm going to move on. So now so far what you got? Ionic compounds, once you add to the water, they split into cations and anions. And because water provides a solvation energy. Cations are surrounded by the water molecules. Anions are also surrounded by the water molecules. And the direction of the oxygen or hydrogen that depends on the cations or anions. And they create the solvation and they create the hydration shell. And this is due to the polarity or dipole of the water molecule. All right. Now here's the question. So we have made a series of ionic compounds. If you make those, I just give you 1A, group 1A, 7A, 6A, 5A. Group 2, 5A, 6A, 7A. Group 3, 7A, 5, 6A, 5A. So many compounds you can make under the sun. Hundreds of compounds you can. Now are they, and also the polyatomic ions, if you put them together, you can make thousands of ionic compounds. You can just name it. Now, all of them are soluble in water? Answer is no. Some of them are, some of them are not. So let's see, there must be some general rule, right? There must be a general rule for the solubility of ionic compounds, and that is here. So general rules of solubility of ionic compounds, and you must remember this. You must read this very carefully for the test. Obviously, test is not a open notes or open things, right? You have to take it, you have to memorize it, you have to understand this. So what are those common rules? All compounds containing sodium plus, potassium plus, lithium plus, group 1, rubidium plus, cesium plus, and ammonium plus are soluble in water. So all group 1 elements, they make a positive charge, including ammonium ion, is a polyatomic cation, all soluble in water. All of them are soluble. Any kind of compound you make, the sodium, potassium, lithium, cesium, rubidium, including ammonium ion, all soluble in water. Must remember, all nitrates and acetates are soluble in water. So for example, if you take a potassium nitrate, aluminum nitrate, calcium nitrate, they're all soluble. Likewise, sodium acetate, calcium acetate, gallium acetate, any kind of acetate compound you take, they're all soluble in water. So remember, all compounds, the sodium, potassium, group 1 elements, any kind of cation, any kind of anion, the polyatomic anion or any kind of anion, they make a compound with a group 1A, they're all soluble. And all nitrates, acetates are also soluble, irrespective of cations coming from group 1A, 2A, or 3A, or even transition metals. Some of the transition metals are also. Most chlorides and sulfates are soluble. Most. Exceptions are silver chloride is a white precipitate. So silver nitrate, if you have a silver nitrate, it is soluble. Silver chloride is not. Barium chloride or barium nitrate or barium acetate is soluble, but barium sulfate is not. That's exception. Likewise, lead chloride or lead bromide, lead iodide, or any kind of lead compound with these halogens, they're soluble in water, but lead sulfate is not. So you have to remember these exceptions. So most chlorides and sulfates are soluble, but silver chloride, barium sulfate, lead sulfate, they're insoluble. Most carbonates, CO3 minus, most carbonates like a calcium carbonate, magnesium carbonate, aluminum carbonate, gallium carbonate, most phosphates, sulfides, S2 minus, and hydroxides are insoluble in water. Exception is the group 1 elements. Lithium, any kind of group 1 elements, group 1 metals, lithium plus, sodium plus, potassium plus, including ammonium. Ammonium goes along with them. Plus, they're all soluble. So lithium carbonate, sodium carbonate, potassium phosphate, lithium sulfide, lithium hydroxide, sodium hydroxide, potassium hydroxide, ammonium hydroxide, they're all soluble in water. So you must remember this. You have to practice it. Please read it again and again. Try to make some compounds and see whether they're soluble or not. Now, I'm going to give you some compound and you tell me whether it's soluble or not, okay? A minute. I'm going to give you some compound right here. I'm going to write the compound and you have to tell me whether it is soluble or not. Everything okay? All right. So let's say aluminum AlPO4. What's the name of aluminum AlPO4? What's the name of the aluminum PO4? AlPO4? What's the name? What's the name of the compound?
Phosphate.
Yep, aluminum phosphate. Is it soluble or insoluble?
Soluble.
Right here.
Insoluble.
So I got one answer soluble, one are insoluble, right? Right here. So most carbonates and phosphates, sulfides, hydroxides are insoluble. So that is insoluble in water. How about this one? Gallium GaOH. All right, OH3. What's the name of this? Gallium OH3. What's the name of the compound? Yeah, is it soluble or insoluble?
Insoluble.
Thank you. Very good. Very good. Now, this one, CaCO3. Calcium. What's the name of this compound?
Calcium carbonate.
Calcium carbonate. Very good. Soluble or insoluble?
Insoluble.
Thank you. Very good. Let's say aluminum, AlNO3 parenthesis 3. What's the name of the compound? What's the name of the compound?
Nitrate.
Yep. Soluble or insoluble?
Soluble.
Yep. Right. All nitrates are soluble. So practice some of those. It's okay. Practice some of those. Practice, please. And now let me give you this one. Fe. This is the last one. Okay. Fe2S3. What's the name of the compound? Yeah. Ferric. I see. Ferric sulfate. Sulfide. Not sulfate. Sulfide. S2 minus. Sulfide. Ferric sulfide. Is it soluble or insoluble? Insoluble. Insoluble. Yeah. Yeah. Now, so that's basically the general rule of the solubility. When the cations and anions are soluble in a solvent, how do they look in terms of the coordination and etc. etc. So you got some idea. Now, basically, I'm going to give you the basic principles, or what are the principles so far we discussed so far, and that's basic principles are, and this is the one you must remember. Many of you are asking what are the basic principles, what are the things that you should deal with it, and for Monday's test, next week's test, Monday's test, and you must remember those things. You must work on those. What is the octet rule? How does it apply when you make any compounds? What is the spin pairing? How the two electrons can stay together? Who can tell me what is spin pairing? Let's see. Let me ask you a question. What is spin pairing? Anyone? Yes? What is spin pairing? Hello?
Is it like when you have one arrow going one way and then the other arrow going a different way?
So one is moving clockwise, another moving
downwards.
Yeah, another moving counterclockwise, creating two tiny magnets, North Pole, South Pole, and South Pole, North Pole. Now they are tracked together. That's a spin pairing. What's the Hund's rule? Who can tell me what's the Hund's rule? Hund's rule.
Is that when it like has the orbitals have to fill up, like the inner ones have to fill up before the outer ones?
So this is the Hund's rule. If you have a subcell and that is a multiple equal energy layers or orbitals, they'll fill up one at a time. One. For example, P has Px, Py, Pz. If you have 4 electrons, it will fill up like this: Px1, Px2, Px1, Py1, Pz1. And then if you have additional electron, that will come to Px. So if you have a subcell has a multiple equal energy orbitals, they will take the electron one at a time before they fill up, go back and fill up. That's called Hund's rule. So if you have another additional electron, that means nitrogen, remember, 2px1, 2po1, 2pz1. Then oxygen, you have additional electrons, now it comes to 2px2, 2py1, 2pz1. So that's called Hund's rule. That's the Hund's rule. How many subatomic suborbitals do you know? How many and how many maximum number of electrons they can hold? Subatomic orbitals. S, P, D, and S, P, D, These are suborbitals or sublevels, F and G. What are the maximum number of electrons they can hold?
Well, am I right that S can hold 2 and then P can hold 6?
I'm writing. You keep going. Keep going.
I don't know the others.
D can hold 5, F can hold 7, and G can hold 9.
D can hold 10.
10.
Aha! Coming up.
14.
I'm writing. 10. Or F can hold how many?
14.
Yeah, someone will be telling me the right answer. And G?
18.
Very good. How do you remember? 2 plus 4, 6. 6 plus 4, 10. 10 plus 4, 14. 14 plus 4, 18. They increase by 4. That is correct. P has 3 orbitals. Sorry, Px, Py, Pz. D has 5. So 5 times 2, 10. F has 7. 7 times 2, 14. G has 9. 9 times 2, 18. Very good. Remember those. What are the basic principles of making ionic compounds and how do they name them? We talked about many, and you must remember those. All there. What can you predict about the solubility of metal chlorides, sulfate, phosphates, and sulfide? I already gave you that. What is the hydration shell? You know that now. Why water shows dipole? You also know that now. From this list that I gave you, if you know these principles and apply it, you'll get at least 10 to 15 questions, at least 10 questions minimum, 10 questions from this. So that means 10 times 3 or 10 times 4 or 10 times 2, whatever is 20 to 40 questions will be right from these principles. And you must work on this principle. And if you have any question, I'm there. Take advantage of my office hours. And any question you have, you work on this weekend for the test.
I actually have a really quick question.
Yeah.
Can you just explain why water shows like dipoles?
Yeah. So what are oxygen, H, and H? That's the water molecule. And this bond has 2 electrons, one from hydrogen, one from oxygen, one from hydrogen, one from oxygen, one from hydrogen. Oxygen is very close to the group 8. It gets only 2 electrons and become negative charge. So oxygen loves electron. It has a higher electron affinity than hydrogen. Hydrogen can donate electron, right? It cannot take electrons. It can in certain circumstances. So hydrogen cannot, so these 2 electrons mostly towards oxygen. Mostly towards, electron is a cloud, right? Electron negative cloud. So negative clouds are towards oxygen. Therefore, oxygen become delta minus, delta, small amount of charge. And hydrogen, since the electrons are going towards that direction, it's becoming delta plus, delta plus. So that's why water makes the dipole. So the dipole. Is it okay? Yeah, sorry. Is it okay?
Yes, thank you.
All right, very good. Now let's apply this. So we know so far ionic compounds. We know what are the things happening there, why they make ionic compounds, etc., etc. We know the solubility of ionic compounds. Now let's apply. Let's get some properties, applications of the ionic compounds, and those are next, right? Sorry, those are this. So some properties or applications of the ionic of the solutions. Solution, we make the solution, right? Remember, we make the ionic compounds, dissolve in water, make the solutions. So some properties of the solutions is as follows. The ionic compounds, once they dissolve in water, they could be electrolyte. If they do not dissolve in water, it could be non-electrolytes. So electrolytes and non-electrolytes. Let's see what are the electrolytes and what are the non-electrolytes. And then we'll come back to the osmolarity, osmolarity, dialysis. We can talk about all those things one at a time. So first we'll talk about the electrolytes and non-electrolytes. What are the electrolytes? Electrolytes are non-electrolytes. The ionic compounds that dissociate in water to generate cations and anions are electrolytes by definition. So what's the definition of electrolytes? Soluble ionic compounds that dissociate in water and generate cations and anions. Water provides the solvation energy to break the ionic force or ionic bond. So that's the cations and anions, right? That's electrolytes. If that dissociation, please remember, if that dissociation is greater than or equal 95% or near complete dissociation, electrolyte is known as strong electrolytes. If the dissociation is less than 95%, that's the partial dissociation, then electrolyte is considered as weak electrolytes. So strong electrolytes, greater than equal 95% dissociation, near complete dissociation, cations and anions. And if it is dissociate less, sparingly, partial dissociation, less than 95%, weak electrolytes. But less than 95%, remember, so it could have a 1% to 94%. So that means even the weak electrolytes, one can consider which is the weakest or weaker, etc., etc. Now, how do you know? How do you do the experiment, or how do you know that that you have ionic compounds in your hand and you dissolve in water? It is a strong electrolytes or weak electrolytes. You can see the dissociation, right? You cannot calculate the dissociation by looking at it, but there are some experiment one can do, or one can look at it visually, whether it is strong electrolytes or weak electrolytes. How? You take a beaker, a container, put the electrolyte, the ionic compounds, and dissolve in water, for example, and add two electrodes, positive electrodes and negative electrodes. You know, the battery has a positive side, negative side, very similar. Add some electrodes in there, and the electrodes are connected with the bulb, light bulb. If what basically happens when you add the electrolytes in the water, it dissociates to cations and anions. Now the cation will migrate towards the negative pole or anode or cathode, and the negative anion will migrate to the cathode, the positive pole. Since they're migrating, they are carrying the electrons, transferring electrons. That's electricity, possibly electricity. And if you pass the electricity from one side to another side, and you have a light bulb, it will glow. So the stronger the glow of the light bulb, stronger the electrolyte. Weaker the electrolyte will give a weak signal or dim light. So that's basically you can test whether an ionic compound is a strong electrolyte or a weak electrolyte. All right, and the non-electrolytes, they don't dissociate, so therefore no current anyway, no electric current and no light, etc., etc. And if you visually can see it like this, so visually you can see like this way. So let's say you have the same thing.
11:52.
Yeah,
it's 11:52
already. Thank you. All right, we'll continue Friday. I'll finish up as much as I can. Okay, bye.
Thank you.
Thank you. Have a good day.
Thank you.